So now we're going to talk about a theorem due to Nielsen and Schwang. And the way this fits into the previous discussion is that we found with our 3-qubit circuit that we could implement 4 different unitary operations on the top qubit. So the top qubit is the thing that we were performing operations on, and the other 2 qubits were where we really had things like programs that said what operator we were going to apply to the top qubit, which I'll call the data qubit. And what we found was that we had 4 possible operations that we could apply. And we also noticed that the size of the space of the program qubits is 4. So that's kind of an interesting coincidence. We could apply 4 unitary operators and the dimension of the space is 4. It turns out that's not a coincidence. And what we're going to do is we're going to go ahead and prove this theorem by Nielsen and Schwang, showing that that really has to be the case. So let me state the theorem first, and then I'll discuss the basic setup, and then we'll go ahead and prove the theorem. I'll write down 2 other statements that are sort of lemmas, if you want, and then use those to prove the theorem. So for each unitary operator implemented by a deterministic processor, an extra dimension of the program space is needed. So for example, if we have just one operator that's going to be implemented, we'll have a one-dimensional program space. If we're going to have 2 operators, we're going to need two dimensions, 3, and so on. So now what we'd like to do is show why this is true. So the basic setup here is the following. I have here's my processor. It's one big giant unitary operator, so I'm going to call it G. And then I have 2 inputs and 2 outputs. The data input is the thing I want to operate on. The program input is going to tell it what to apply to the data. So the output should look like this. I should have the unitary operator acting on the data state, and the program state can get modified when it comes out. And so I'm going to call that P prime UD. And the reason the D is there is that in principle, how it gets modified could depend on the data state. Now the 2 statements that I want to go ahead and prove, which then actually prove the theorem, are the following. So number 1 is that the state P prime U D does not depend on D. So even though I've written the D here, it turns out that that's not necessary. The second one is that if P, U, let me call it 1, and P2 are programs, for different operators, then they have to be orthogonal. And that's the second statement actually proves the theorem, because if every time we add a new operator, it has to be orthogonal to all the ones that are already there, that means we need an extra dimension. So that by the time we get through proving these 2 statements, we will have proved the Nielsen and Schwang theorem and show that every time we want to add a new operator, we have to add a new dimension to the program space. So it's going to keep getting bigger and bigger and bigger the more operators that we want to be able to perform. Now let's go ahead and prove number 1. So I'm going to write down what happens to two different data states, but the same operation. All right, so I would have G acting on D1 PU is equal to, and then I'm going to have U acting on D1 and then I'm going to have P prime U D1. Then I'm going to just do it for a different data state, and I'm going to have G D2 PU equals U D2, and then P prime U comma D2. Now what I'm going to do is I'm going to take the inner product of one equation with the other. And when I do that, what's going to happen is the following. So on the left-hand sides, I'm going to have a G dagger G. G is unitary, so G dagger G is in fact just equal to the identity. So that and then I have the PUs, which are simply the same state, so the inner product of this state with itself is just 1. So on the left-hand side, I get D2 D1 is equal to, and then on the right-hand side, I have now the U dagger U. Again, U is unitary, so U dagger U is equal to the identity. And then I will have a D2 D1. And then I'm going to have the inner product between these two things. So that will be a P prime U comma D2 P prime U comma D1. Now, if D2 inner product D1 is not 0, I can cancel it out. So then I just get that 1 is equal to P prime U D2 P prime U D1. And that implies, since these are all unit vectors, that P U prime B2 is in fact equal to P prime U D1. So the output is the same for both D1 and D2. And that means really that the output simply doesn't depend on whether I have D1 or D2 here. So the output program state does not depend on D, which is exactly what I said there. So now we want to go ahead and use that to prove number 2. And you'll notice in number 2, I've written the, well, I haven't here yet, but when I do prove number 2, I'm going to remove the D dependence on the P primes. Now we want to go ahead and prove number 2. And you'll notice we've made a little notational change here where because we proved number 1, we removed the D on the output program state. So it's now just only depends on the operator. So now what I'm going to do is I'm going to write down, very similar to what I did before, but instead of 2 different data states, I'm going to have 2 different program states. So we're going to prove 2. And so let's write down our 2 different operations again. So we're going to start with G, and we're going to have D, and then we're going to have PU1. And then that is going to equal U1D times PU1 prime. And then we're going to write it down for a different operator, G, D, PU2 equals U2, D, PU2. And then we're going to do the same thing we did before. We're going to take the inner product of both sides of the equations and see what we get. So as before, with the left-hand side, when I take the G's, I'm going to get a G dagger G, and that's, again, just going to be 1. The D's are the same state, so that will also just give me a 1. So what I'm going to get on the left-hand side is I'm going to get that P U2 P U1 is equal to, and oops, there we go. Then I'm going to get a D and then a U2 inverse U1 D, and then I will get a P U2 prime, P U1 prime. Well, what does this tell us? So let's assume that P U2 prime, P U1 prime is not zero. So assume so that means I can divide by it. So let's go ahead and do that. So if I divide by it, what I'm going to have is I'm going to have over here that P U1, P, that's a U2 actually, P U1 over P prime U2, P prime U1 is equal to D U2 inverse U1 D. Now what does this tell us? You'll notice that the right-hand side of the equation depends on D, but the left-hand side does not. So what that means is that since this does not depend on D, this can't depend on D either. And the only way that that would not depend on D is if the operator U2, U1 is simply a multiple of the identity. So this implies that we have to have that U2 inverse U1 is equal to some constant C times the identity, because that way I would just have some constant times the identity there, I just get dd, and the D dependence would disappear, which it has to do because the left-hand side doesn't depend on D. And now this whole thing is a unitary operator, which means that the C has to obey C is equal to 1, so I can just write C equals e to the I phi for some phi, and that simply implies that U1 is equal to e to the I phi. So multiply both sides by U2. So the operators are just multiples of each other. That means it's basically the same operator. Now, so where did that come from? That came from the assumption that P prime U2, P prime U1 was not equal to 0. So if that is true, then the operators U1 and U2 basically have to be the same. But if this is 0, then what's going to happen, if I go back here, if that's 0, then that has to be 0. And that proves what we want. That the only way the operators can be different is if this is true. So that means that they have to be orthogonal to each other. Okay, and that proves the Nielsen and Schwann theorem.